Let me join other speakers by thanking the organizers for putting up this nice workshop and giving me a chance to speaking here. It's great to be, at home and in Seoul at the same time. And well, essentially, the thing that I wanted to tell you today is about a paper that appeared before summer in collaboration with my students David Prieto and Max Wiesner, which explores certain aspects of F-theory flux vacua in the regime of large complex structure. Okay. So, okay, we have roughly 50 minutes ahead. So let me begin by introducing why this problem is interesting. I think that F-theory flux vacua is not a new subject at all. It has been going on for many, many years, especially, well, the past 20 years. But, well, modular stabilization is a kind of a subject that is a little bit very passionate, right? Like everybody cares about modular stabilization all of a sudden, and then nobody cares about modular stabilization, and they care again. And so it goes on and off. So let me just a little bit try to review how the subject goes from my personal viewpoint and also from what's going to be important in the next few minutes. So one very natural way to motivate this subject is to look at one particular corner of the string landscape, and which is type 2B flux compactifications. This is not the only corner where modular stabilization occurs, but it gained a lot of attention after the paper of Gidding, Katra, and Polchinski, because in this particular setup, you have a very nice mechanism for modular stabilization that is kind of intuitive and kind of powerful, because you stabilize a bunch of moduli with just one extra ingredient to the usual Calabi-Yau compactifications, which are the free-form fluxes. Well, one of the results of this scenario is the proposal that came afterwards for full model stabilization strategies, the well-known KKLT and large volume scenarios. And in this context, which again has created a lot of activity over the years, this mechanism of free-form fluxes stabilizing a bunch of complex structure and dilaton moduli in type 2B was seen as well, the first step toward the full model stabilization mechanism. So Joseph, in his talk, he also classified this KKLT or LVS procedure as a step 1, 2, and 3. This would be step 1, right? And from all the steps, this is supposed to be the easiest one, the one that nobody would challenge or question until very recently. Because the math was kind of simple. No, you just have this F10 potential. You have some equations. You find solution to the equations, and people start finding solution in simple cases. And this more or less convinced everyone. It was the other two steps that created more controversy, but not this one until recently. And is it until recently that triggered the paper that I want to present today. Very good. So let me just point out, in this spirit of reviewing, a few strong points and weaknesses of this type 2B flux compactification with free-form fluxes, like complex structure model stabilization, etc., etc. So one nice thing, which was already in the paper of Giddings et al. And before, is that, well, the uplifting the setup to a theory is kind of trivial, right? You just go to a fourfold, and then you have a four-form flux, and then, well, you have the Guk of alpha Witten superpotential, and everything goes. Something that came afterwards by Douglas and other, is that with this mechanism, you could develop the statistical intuition and statistic picture of how vacua are distributed, how many are they, how do they grow with certain quantities of the Calavia compactification, et cetera, et cetera. So this gave some substance to what would be the ensemble picture of vacua, and is essentially based on the distribution coming from compact structure and dilaton model stabilization. Now, some things that are not so reassuring is that, okay, the equations in abstract are kind of there, and then you can see that you are going to have a, well, same number of unknowns and same number of equations, but the full analytic control, it's very hard to maintain when you go to large number of moduli. And by large, I mean 3 or more, right? Like for 2 moduli, people have found solution for 3 moduli as well. But then afterwards, if you look at the huge literature of type 2B flux compactification, you have to resort to some sort of argument. You have to make truncations to say that these fields are going to be fixed at this value. You have to take symmetry arguments for this truncation. I mean, you have to do some gymnastics to effectively reduce the number of moduli to 2 or maybe 3. Otherwise, the potential becomes crazy, and well, you don't know how to find solutions in a reasonable way and with a minimal amount of pages for your paper. There's exceptions to this, like K3 times K3. I mean, well, thanks to the simpler equation to the factorization of the geometry, then you can push the algebraic description of your flux vacua equations further, and then, well, in there, even if you have more than 3 moduli, then you can solve things algebraically, as several papers have explored. Okay, which I am omitting here. Sorry for that. Now this, you can say, okay, well, I don't care for my equations with the maybe the dilaton and the overall compact structure models, then I get a picture of what I want to do. But well, in practice, it's nice to know where, I mean, having the whole picture of this multi-field space. And in some cases, you want to have hierarchies between your fields. For instance, to obtain scenarios that are needed for some of these full model stabilization scenarios, like having a small W naught. For this, you need some hierarchies, you need some asymmetry between the vevs of your moduli, and these symmetry arguments or these truncations typically fail to achieve that. Well, there has been some progress in the in type 2B setup to achieve these things, like an emerging picture of how you may do it. And this typically involves dealing with more than 3 moduli. You have heard some of it in Liam's talk. But the idea is that we want to go further on this direction, and we want to do it in the FDRE setup. Okay, that would be more compelling. In moreover, some things that do not fully add up, like, well, they are kind of counterintuitive from the pictures of what we have in early 2000s of compact structure model stabilization, is that people have recently started looking as how many moduli are stabilized. Generically, you would say all of them. But the point that they have raised is that in some cases, when you try to stabilize all the moduli, then you induce a tadpole to the fluxes that is way too large to what you would like to have for your scenario. And in some cases, it's way too large to have a supersymmetry vacuum. You have heard about this in Josif's talk, and this is something that I will have much in mind during my talk. These two points, actually, the relation between the tadpole and the number of moduli, and trying to get analytic control. Now, with this in mind, one also has to take into account that recently there has been a change in the picture, or like new techniques have been available. And this is summarized by a number of papers, but perhaps the closest to the talk here is a paper by Greenlee and Valenzuela. in which they apply the techniques developed a lot before and by several mathematical papers, in which you get a general idea of the universal properties of the periods at asymptotic limits in construction moduli space. So in the F theory setup that I will consider later on, they managed to have a thanks to this universal property of the periods that govern what the superpotential and the Kerr potential are, they managed to have a general classification of the flux potentials for F theory flux compactifications. But this is something that grows very quickly, so they essentially do it for one or two moduli. Moreover, as you have seen in Thomas' talk, these kind of techniques, like they have a multi-purpose applications, and they also serve to argue for the finiteness of flux vacua. Like when you map the lattice of fluxes to the minima, you don't get an infinite number of them, as you could naively suspect. Good. Well, while this this approach of Riemann collaborators is quite general when applied to F theory flux vacua. In here, I will focus on a very specific region of complex structure model state, which is the large complex structure, which is one of the best understood or better known, and has led to many scenarios because of its simplicity. And it has two advantages, as Thomas mentioned in his talk. First, we don't need the this what he called essential instantons in his talk to get a well-defined field metric to do all the computations for things to make sense, if you want. And I will be avoiding that. And second, it is mirrored to naturally mirrored to type 2A at large volume. And this second aspect is very precious to me because I can extract a lot of intuition out of it. What I mean by this is that the type 2A flux potential at large volume is something that has been known for some time already. These two papers papers from the early 2000s, but recently it has been reviewed on a new light, which is, at the beginning it may sound a little bit silly, which is just a rewriting of the scalar potential, but at the end it turns to be very powerful, both at the physics conceptual level and at the application level. So let me just very quickly say what I mean by this. The upshot is that you can show that the type 2A flux potential at large volume can be written as a bilinear. You see my cursor, right? When I wiggle it, or you don't?
Yeah, we see it.
My pointer. Do you see my pointer when I?
Yes, I do.
Okay, good. So you can write it like this, which is a extremely simple form, and it has a nice feature that, at large volume, all the bulk fields separate between axions and saxions, all the complex fields. And this bilinear form has a feature that the saxions appear in this quadratic symmetric matrix, and the axions and the fluxes of the compactifications appear in this vector of quantities, okay, which is a polynomial. So with this simple form and this separation between axions and saxions, you gain a lot of power to understand how your vacua are in this regime. First, there's a physical meaning behind that, which is that the factorization, the dependence that one kind of fields go here and the other kind of fields go there, is due to the fact that you have approximate axionic shift symmetries in this regime, and that you are neglecting the exponential terms. As I said, this is something that I will be doing, unlike what Thomas is in part of his talk. Another physical important aspect is that this quantity, this symmetric matrix, what it's doing is encoding the kinetic terms of the free forms of your four-dimensional theory, the three forms that couple to the membranes, and therefore this is encoding what the four-dimensional membranes of your compactification well, couple, what the tensions are. While these guys in here, these are objects that are invariant under the discrete symmetries, the discrete case symmetries of your four-dimensional compactification. From the 10-dimensional viewpoint, you may see these quantities, which are combinations of quantized fluxes and axions, as a dimensional reduction of what we call gauge invariant fluxes in our 10-dimensional supergravity description. Basically what you're doing, instead of writing a potential in terms of quantized fluxes and a bunch of fields, you are writing things in terms of gauge invariant fluxes, which are not quantized, but are gauge invariant, and a bunch of Saxions, okay? And then, well, finally, you can see that this thing has to be bilinear because you are starting with a two derivative action. So one flux per derivative. So two derivative, I mean, bilinear object. So of course, when you go away from this regime, from this approximation, you will get corrections to this, but they should be suppressed in this regime, and then you can proceed with your analysis. Now, this is the physical meaning of what this silly formula means. But then there's an application which consists on finding vacua based on this form, and this has been shown to be quite successful. I mean, it has allowed to repackage previous results and obtain new ones in the systematic search of flux vacua, both for Minkowski and ADS in type 2a, to classify solutions in terms of branches of vacua. And this is actually an approach that you can generalize when you include not only Calavilla with fluxes, as initially, but also geometric, non-geometric fluxes, F-term potentials, D-term potential, etc., right? So, well, the thing is that if you look at this, the list of items in here, they are essentially based on a four-dimensional intuition, and all the items listed here, they will also apply to other contexts like type 2b. So this is not this form that is explained by all these items is not unique of type 2a. It would also happen for type 2b. And so the idea that I will be pushing during the rest of the talk is to apply the same bilinear form of the potential and pushing these consequences for type 2b and F-theory vacua. Because everything that I have said about type 2a will most of it apply to type 2b or F theory. Now, let me just say briefly which kind of things I will be looking at, okay? I will not be the most F theory compactifications because I will be looking at the smooth Calavilla fourfolds. And I will be, again, focusing on the large complex structure limit, in which, like in type 2F large volume, we have a plethora of axionic shift symmetries and all the complex fields, all the complex structure fields of the F-theory compactifications split into an axion plus a Saxion. When you do that, you have two kinds of potentials, the F-term and the D-term potential. Here, just like the green metal paper, I will be focusing on the F-term potential, which is also the one that has given rise to most of the activity and where all the scenarios of full model stabilization start from, right? So this is the 20-year-old, more than 20-year-old Gukov-Afawit superpotential with the Kerr potential that we all know and love. And that gives rise to this very simple, very simple looking scalar potential. But that in practice, as I say, when you just want to include in here how all the fields behave, can become kind of a nightmare. Okay, so this is the idea. Bilinear applied to type 2B F theory and see what happens. So the first step of this talk would be to describe how the flux potential looks like. As I said, well, typically what we do is we look at the two main quantities that determine the F10 potential. This is the Kerr potential and the superpotential. And then what, as anyone working on this field knows, everything is determined by the periods. No, that's why the approach of Green metal is so powerful, because you know information about the periods and you know a lot of things. Once that you know what the periods of the holomorphic four form is, well, the superpotential gets this simple form, and most of what is going on you already know. You only need to specify the flux quanta, and then you know what the periods are as a functions of the fields, and well, then you're done. Now, in this context, when you want to go full F theory fourfold, things become a little bit more tricky, in the sense that, well, you need to tell me what the four cycles, which four cycles you are looking at when you integrate omega. Not all of them are good for the book of Witten superpotential, because not all the four cycles couple to omega. The guys that couple to omega and will give you a non-trivial contribution to the superpotential is what is called the horizontal cohomology that comes from omega and its derivatives. Okay. So to overcome this technical issue, what we do is we follow the same philosophy of Cabo, Bisset, Clem, Tota et al., and use four-form mirror symmetry in type 2a to compute these periods in terms of central charges of B branes on a mirror fourfold. What happens at the end of the day is that when you do that, the Bukov-Witten superpotential looks like this, which is just like the Taylor-Rafa superpotential, but an analog in four complex dimensions, four complex internal dimensions, plus, well, curvature corrections and so on. And then when you have it of this form, then you can proceed with the analysis, okay? I'm not gonna go on the technical details, just gonna flash how the periods look like when you go to the asymptotic limit in large complex structure. There's, in general, we have polynomial corrections which involve smaller powers of the complex structure fields, and then eventually exponentially suppressed corrections that I'm going to ignore all over in this talk. The only thing that I want to point out here is that you have at leading order, you have a relatively simple expression for your periods that depend on, well, there are polynomials on the fields, which coefficients which are topological quantities, integers that are defined in the mirror fourfold. So basically, this QIJKL is some quadruple intersection number, and then this issue of selecting what the horizontal cohomology is basically done in the mirror as well by generating four cycles via intersection of divisors and parametrizing a basis in terms of also these intersection numbers. Okay, so we have let's sum it up. We have some explicit expression based on the topological quantities in the mirror fourfold. But with this, we can proceed. We have a superpotential in which you see how the flux quanta enter EEM, these are the flux quanta, and then you have multiplying the periods of the same form that we all know and love. Finally, you can also compute the Kerr potential, and you get this simple expression that is also some simple generalization from the type 2b expression, in which all the shift symmetries that we were talking about are manifest because nothing depends on this axioms P, which in the mirror would be the B field. No? And here, well, there are some some axioms. Well, so this is very nice, but this is so far nothing has changed. I mean, we just use some expression for the periods, but nothing has changed from the usual philosophy in which one computes the flux potential and analyze the flux. Okay, so this is concrete, but is the same spirit as always. Now we want to do something a little bit different, and something a little bit different means, good, I have this expression for the superpotential. It's expressed in terms of the flux quanta and the periods, and typically you give a lot of importance of the flux quanta and the periods separately. We don't want to do that. What we want to do is to express the flux potential in terms of monodromy invariant quantities, and neither the flux quanta or the periods are monodromy invariant. What are monodromy invariant are combinations of fluxes and axions, and we want to express everything in terms of them. Superpotential is monodromy invariant, but not the two things that you contract in order to get it. So one way of understanding what we are doing is take the four-form flux, okay, which is a bunch of four forms, integer four forms multiplied by integers, the flux quanta, and rewrite it in a different basis, in which I try this four-form alpha by some alpha tilde. This new basis, what it's going to be is going to come from linear combination of omega and the derivative of omega and the conjugates, in order that I will have a real basis with the same intersection numbers as before, but now these guys are all monodromy invariant. When you do that, automatically, the coefficients of G4 expressed in this basis, because they are also monodromy invariant, because G4 is also monodromy invariant, of course. And it's these coefficients and not the quantized fluxes that are going to be the stars of this talk. I'm going to express everything in terms of them, and I'm going to get a simpler picture. Well, simple picture, what you have to swallow is the expression for these guys. I flash them here. I don't pretend anyone to. I don't want anyone to learn them because they give you a headache. But essentially, you get the idea that instead of E, I have this guy rho, which is a bunch of fluxes. This is linear on the fluxes and increasing polynomial on the axions. And same here, same here, same here. This is kind of expression that we also got in type 2a. And well, using them is applying the same philosophy as we have in type 2a for finding flux vacua. So what we do is to write the flux. You can compute the flux potential as always, but then we write it in terms of these guys. And when you do that, amazingly, you get a one-line expression for the full flux potential for arbitrary number of moduli. Okay. So, which is a huge simplification compared to what you get in the flux literature, in which people will just deal with the vacuum in terms of what the supersymmetric conditions are. This is a very, like all things considered, is a very simple expression for the scalar potential. In here, you can see that it's quadratic on these rows, which are the flux Saxion polynomials, and then it's multiplied by a bunch of quantities that are obtained from these topological quantities in the mirror, contracted with the Saxions. Okay, and this is a natural metric that appears in Calabi-Yau fourfolds. Very good, but this is not everything. I promise that, well, you can get some intuition out of it. So let me just write it in a simpler way, how this flux potential looks like. When you write it in this form, this matrix looks as simple as this. So diagonal and anti-diagonal. The diagonal piece is essentially the Hodge-star metric acting on the different form, these monodromy invariant forms. I mean, you need them to be monodromy invariant for the metric to have a well-defined monodromy invariant action. And this is essentially the intersection numbers of the four forms. Okay. And yeah, well, this is, as you see here, this is super simple. This is because we have, we are describing the periods in a simplified, I mean, in a simplified asymptotic limit in which we only keep one, the leading term for each of the periods. In general, it will be a bit more complicated, but the main idea is that, well, we have a description for the Hodge-star action in a very particular basis of four forms. And this is what is going to simplify the whole discussion in what comes next. To be fair, and to push the picture a little bit more, I cannot only deal with this expression for the period. This is just an approximate expression. When I go a little bit away from the large complex structural image, which I will want to do, I need to include first polynomial corrections and then eventually exponential corrections. In this talk, I will only include polynomial corrections, and I will assume that I am some large complex structural limit in which exponential corrections can be safely ignored. This means including some lower polynomials in here. But the intuition of what I'm doing is again better understood in the mirror fourfold, in which these corrections come from curvature corrections that you can, well, they will modify the central charges of B-branes. Then this will be, there are essentially two classes of corrections, the one that are quadratic in alpha prime. What these guys will do is kind of harmless. They will just modify the flux quanta by which I start describing everything. So we just a redefinition of the flux quanta, the coefficients, and therefore the rows, my description. And then there will be another one, which is the cubic in alpha prime in the mirror, that will correct the field metric and therefore this matrix Z. You can, first of all, see how these corrections go by looking at the correct expression for the Keller potential, which is essentially what we do, what they do. And then you can see to the leading term, you will get this correction in which this guy I3 is this topological quantity, okay? This expression generalizes the well-known curvature corrections for the Keller potentials in type 2b and in type 2a, and it's just, well, including more of this alpha prime corrections because we have a fourfold. Good. So, well, let me recap what I'm trying to do here. The main goal of this work is to gain analytic control. Okay, have more analytic control, know what we are doing with equations without resorting to codes and numerics and so on when we stabilize complex structure moduli in type 2BF theory. Nothing about ADS vacua, nothing about uplifting, only complex structure dilaton moduli. So strictly speaking, these are not vacua yet, but well, this is where the subsequent discussion would come. But let's first look at how things look this level, because this will, for instance, impact on the distribution of vacua when you have a full modular stabilization scheme. The main technique that we are using, based on papers of Klemov collaborators, is to describe the periods at large complex structure using fourfold mirror symmetry. And the philosophy, once that we do that, is to express the potential, the flux potential in a bilinear form that does two things. First, it separates the dependence of axions and saxions. And second, it depends on monodromy invariant quantities. Okay. So what will happen when we do that? Well, the consequence is that this will be the second part of the talk, is that the vacua equations will become algebraic, that the difficulty to stabilize 1, 2, or 200 moduli in terms of equations will be essentially the same. And we will get a very simple form for this bilinear matrix Z, as you have already seen, a large complex structure, and this will be corrected by polynomial terms that we will can treat in perturbation theory or any other way. Eventually, what we want to do is to classify different branches of vacua. I will give a partial description of that. We didn't do a thorough job, but we already got some results. So I don't know if there are any questions so far, or shall I proceed?
May I ask you one question?
Sorry?
Go ahead.
Yeah. So if there is a mirror symmetry in fourfold, then what are changing? The Hatch numbers are changing, or?
Yes.
Eh?
The
yes.
numbers are changing, yes.
So Hatch numbers is how it's changing? How are they related? Yeah.
I think that you exchanged H3,1 by H11, if I recall correctly.
That way. Okay, thank you.
No problem. Okay, so if there are no more questions, but let me just say that I'm not doing for mirror symmetry in F theory. This is in type 2A. I'm using type 2A as a artifact to obtain this information for the periods. So physically, the fourfold mirror symmetry would apply to type 2A compactified to 2 dimensions. Okay, so what did we learn from this strategy. Let me just try to summarize. This will become slightly more technical, but I'll try to go easy over it. So first, as I promised, the flux vacua equations are algebraic. I start with this form for the potential. This is positive definite, and as one can check, the vacua equations are as simple as this. End of the story. You tell me what this matrix is, you tell me what this guy is, I give you the equations. At leading order, before taking into account the polynomial corrections, because I have this matrix that is block diagonal, I get a very simple equation, 3 independent equations, which are this. You remember that is this quartic polynomial on the on the Saxions that has to do with the curve potential, and then these guys are also defined by quadratic with Saxions, but the expressions are fairly simple. This is what it is. If you want to have supersymmetric vacua, this is something that you can also implement. You have to add these 2 extra conditions, and then if you solve them, you will find a supersymmetric vacua. Of course, these are more difficult because you are imposing more equations in the same number of unknowns. Now, you can add the polynomial corrections, and then your equations become more complicated. This will be, I mean, this is a little bit of a headache, but it will be important in following. So let me flash how they look like. This is essentially the expansion parameter that you, natural expansion parameter when you include polynomial corrections, is epsilon. And then you can see that, well, when you include the full, I mean, when you write down these guys, the equation of motions for the corrected flux potential, you get a more complicated expression, which at first order in epsilon looks like this. So this, instead of being 0, like in here or in here, well, you get this linear dependence on the epsilons. Good. Then there is the tadpole constraint, which, as I motivated before, has raised a few comments with respect to complex structure model stabilization. So the tadpole constraint is also well known and read as follows. We need that the number of, I mean, the D3 brane or M2 brane charge induced by the fluxes and the number of D3 branes equals the Euler characteristic of the fourfold divided by 24. And we need these 2 guys to be positive numbers, which means that the flux-induced charge, which is this integral, is smaller than the Euler characteristic divided by 24. In our language, this flux-induced tadpole looks like this product of fluxes. And then you can check that this is exactly the same as this product of flux axion polynomials, these gauge invariant quantities. Now, this has a bunch of signs. This doesn't tell you if this is positive or anything. Anything can happen. But when you impose the vacua equations, you see that the flux induced tadpole, it becomes a sum of definite positive quantities. No, okay, so this is square, this is square, this is square. This is the same thing as saying that in vacua, G wedge G4 equals to G wedge star G4, and this is a bunch of positive things. Now, the point that we want to make sure is that this thing is bounded from above. For a fixed Calabi-Yau fourfold, this will have some value, and we cannot go on implementing fluxes that give you an infinite, I mean, a very large, arbitrarily large value for the flux induced tadpole, because then we will not be doing anything. Also, if you recall Thomas' talk, this play a very important role in arguing that the number of flux vacua is finite. So this is something that we want to take into account by all means. And what happens? What we can do is to say, okay, let's assume that our vacua are on a region of large complex structures. Let's take one complex structure, let's take it to infinity, and let's ask ourselves if we find vacua or not. This is a very rough estimate. Like, there are better classification techniques, but we wanted just to have a good idea of what could happen. Okay. So if by taking some limit, some particular limit, this limit, some ti going to infinity, this expression blows up, we will not find any vacuum, okay, for a fixed Calabi-Yau fourfold. What happens in practice is that when you start taking this limit, you have to put some of the fluxes to 0. For instance, this thing will always grow when we take this limit or even more complicated limits, no, that take some one or several quantum structure to infinity. So this means that necessarily this coefficient has to be 0, which means that some fluxes have to vanish. This is a result that was already pointed out by Marshall and Sousa. But we can go on and look at the other terms and see if something more stronger should happen. No? The next thing is to look at this term, this product of these two things, and see when you take a limit, take some guy to infinity, it's bounded or unbounded. Again, this is where we have done a very rough classification, but using the techniques that Thomas was telling us about yesterday, or also Timo has been looking at. One could do a better job, and I encourage everyone to do that better job because we were a little bit lazy in this point. So what we found by doing this rough estimate is two cases. There are probably more. The first case is when some field appears linearly in this quartic polynomial Q, or inside the Kerr potential log, and we take this field to infinity. So in this case, we may keep this flux, the corresponding flux, different from 0, but all the other guys that appear in this term must vanish. Otherwise, we will the flux in this tadpole will blow up. This is what we call the linear scenario because of this guy appearing linearly. Now, when this appear quadratically or higher, perhaps there are other options, but a safe way of guaranteeing that there could be vacua or a necessary condition, safe way of writing down necessary condition for vacua is to set all these guys to 0, all of them. Okay, so this term would also vanish, and we will only be kept with this term. So this is what we call the generic scenario because we are doing like a very crude killing of fluxes. So in this generic scenario, we have a flux vector in which several entries are 0, this one and this one. And the leading vacua equations simplify even further, and the tadpole is just this term. Okay. One nice feature is that the equations for Saxion and Saxion decouple. And this simplifies how the solutions look like. What happens at the end is that you can define a matrix based on built from topological quantities and fluxes. And the rank of this matrix is telling you right away how many fluxes are, how many fields are being stabilized, are being fixed, which is a huge simplification compared to the previous pictures in the literature. At leading order, you, if R is the rank of this matrix, you find that you stabilize R axions and R minus 1 saxions. So you never stabilize everyone. But then when you take into account polynomial corrections, you stabilize one more saxions. And then if the rank of R is maximal, you will be stabilizing everyone. The price to pay is that because you have used polynomial corrections to stabilize the Saxion vevs, you cannot do this as arbitrarily large complex structure where these corrections will be negligible. So you have a bound, effectively you have a bound for the Saxion vevs that is summarized by this formula, for instance. Now, because most of this model stabilization business has been going on in type 2B, on which the other full model stabilization scenarios are built, let me apply this philosophy to the type 2B limit. By type 2B limit, I will be meaning that you have the usual Calabi-Yau orientifold. And then the moduli are the bulk moduli of the Calabi-Yau orientifold. So essentially a theory on this manifold. This implies neglecting these membranes either because they are not there, or they don't have moduli, or they don't affect the bulk dynamics, or you just fix them like in the orientifold limit of K3. Like this is what most people do in the literature, type 2B literature, and we want to connect with them so that we take the same approach. So when you do that, then the complex structure moduli naturally split into two sets. One is the axial dilaton, and then is the complex structure moduli of the threefold base. And the quartic intersection number of a mirror, they be called the triple intersection numbers of the mirror base. Now the flux tadpole looks like this. It's a little bit more complicated. You have more rows. Well, okay, you have to distinguish between H flux and F3 flux. But the gain is essentially the same. You look at these terms, you see if any of them blows up when you go to some limits, and you try to classify branches of vacua in terms of them. You can do it a little bit better in the type 2B, but again, we did a crude estimate, and I encourage again everyone to make a better job. So for instance, you can take the limit in which you scale the axial dilaton with this cubic polynomial of quantum structure Saxions with some power to the q. If q is smaller than 1, which means that, well, this guy essentially win, then you need to, then by analyzing these coefficients, you realize that all these guys have to be set to 0, and you are in the analog of the generic scenario applied to type 2B, which we call type 2B1. But if this guy is 1 or bigger than 1, then you set to 0 other guys, and you end up with what we call the linear scenario, or type 2B2 in this setup. Okay, so again, like these are 2 branches of vacua out of probably more, but these are the ones that we found and try to understand a little bit better. So the type 2B1 vacua, we haven't analyzed in full detail, but from our general expressions, we already get some formulas that allow us to connect with previous works. Some of them have been presented in this conference. You start with a flux vector that has a bunch of zeros, a flux tadpole that looks like this. And then the matrix that tells you how many moduli you are stabilizing looks essentially like this, where this SAB is this contraction of fluxes and topological invariance. So for full moduli stabilization, you need this thing to be maximal rank, means S invertible, and this quantity different from 0. And then, well, you can find the solution for the axions, also for the Saxions, although they are more complicated and so on. Now, one fun fact, whenever this is not maximal rank, but maximal -1, then you will have one flat direction. One particular way of getting this is taking that this S is equal to 0. And then you find a flat direction along this value for the moduli, which is exactly what the Mirtas et al. Found a couple of years ago. You can go and try some flux ansat where you will know that you will have full model stabilization because this guy is of maximal rank. This would, for instance, one of them would look like this. Funny enough, this implies this relation for this matrix, which is exactly what Banco Pillado et al. Propose as a truncation ansatz to simplify the modular stabilization in type 2B large complex structure and obtain a simple mass spectrum. So you see that by using this very silly matrix, you can connect with different results of the type 2B literature that have tried to describe how flux modular stabilization and flux spectra and so on and so forth work for arbitrary number of moduli. One interesting thing is that in this ansatz, in this one, I don't know, in general, I don't know for this generic scenario, but in this one, all these summands of the flux tadpole are positive. So which means that the flux tadpole will grow at least linearly with the number of moduli. So this is exactly the kind of behavior that Joseph was pointing out the other day. And that would give rise to what they call the tadpole problem. I don't know. We failed to see if in a more general context this is also the case or not. The equations that as we use them or as we have analyzed it didn't tell us one way or the other. But at least in this case, let's say for this ansatz of the paper of Blanco Pillado et al., this would happen. So in this setup that they look at, well, the tadpole problem will be realized. Now the type 2B2 vacua, this is a different beast. You put the quanta to 0, different quanta. The flux is much simpler. It's a product of 2 integers. And these are in fact vacua that are dual to type 2 Minkowski vacua that were pointed out already a few years ago in the literature by Paltita, Sinato, and Ward, and then reanalyzed from the viewpoint of bilinear and invariance in this paper recently. Now you can, here in this case, you can write down the vacua equations at all orders in the polynomial corrections. They look like this. You can also expand linearly if you want. And these are the solutions, which is basically taking them from this type 2A picture. To the educated reader on flux quantification in all corners of the landscape, you will see that these equations, they pretty look like a lot, the stabilization of a complex structure moduli, like the equations that appear in type 2A Calabi-Yau flux quantification, the setup of the Woolf et al. And finally, in this setup, you also find a bound for the Saxions. The Saxions kind of have arbitrarily large value because, well, essentially because you are again using flux, polynomial corrections to stabilize a moduli. If you remove the epsilons, you set them to 0, you will not find solutions, or better say, you will find solutions, but you will have to impose conditions on the fluxes and will give you flat directions and so on. So full model stabilization is only achieved when you do polynomial corrections, and this gives you a bound on the Saxions. So I think I'm running out of time, so let me rush to the end. One interesting point of this type 2B vacua that have raised some controversy is that they seem to give a counterexample of the tadpole conjecture, because, well, the tadpole itself, the contribution to the tadpole, is just a bunch of integers, and this is the same for an arbitrary number of moduli. So the question is, and the question we try to ask in the paper is, one can do this not only in type 2B, but in more genuine F-theory context. And the answer that we found is that, well, again, the key ingredient is that there is one field that appears linearly in the superpotential and this exponential of the minus square potential. And you can engineer that geometrically when you consider a mirror fourfold that is a small Calabi-Yau 3 fibration over P1. So we look at some examples and so on. I mean, one could look at the others, but this is what the picture is. So the equations, when you, I mean, I'm not going to write them down, but the equations look very similar to the type 2B vacua that I just presented. And then whether you have Saxion bounds or not, well, depends if you really need the polynomial corrections to stabilize your moduli or not, which it depends on the case. Some cases will happen, some cases will not happen. So this leads me to the last point, which is these Saxion bounds that we find. What do they mean? What do they imply? Okay. As I already said, the bounds of the Saxion of BEVs or vacua, the fact that you cannot find vacua beyond some value of BEV when you go in one direction or the other, means that in practice, some moduli are only stabilized when you consider these polynomial corrections. Okay. So beyond some regime, you don't find anything. This is quite interesting from some of the lessons that we learn from the statistic picture of type 2B vacua. Because if you consider the maximal rank of M, you will have, you remember the Saxion band will look like this. And this growth with the tadpole to the number of complex structure moduli plus the dilaton is very reminiscent of the statistical growth of vacua as found by Ashok and Douglas, and then Neff and Douglas. Also, when the rank is not maximal, well, then the polynomial corrections will not fix all moduli, but then you may argue that exponential corrections may do that. And in the same sense that the polynomial corrections take you away from the asymptotic large complex structure regime, the exponential corrections should take you to the small complex structure regime, at least for some moduli. Some, as Thomas was also saying, some intersection of large complex structure with conifold or so on and so forth. No? This seems to be the key from our viewpoint to find hierarchies on quantities like W naught. Okay, but I mean, we say this by our like how we rederive the scenario of the Mirtas et al. And also the recent paper of Thomas from our equations. So, well, that was all. Let me just summarize what I've tried to convey in these minutes. Our point during this whole time was to write the F-theory flux potential as a bilinear of monodromy invariant quantities. This gives us analytic control for arbitrary number of moduli, which was something that mostly lacking in the literature, and one had to resort to all kind of gymnastics that were admittedly ugly. The power is that vacua equations become algebraic, and so one may implement the same kind of techniques and pictures and precise pictures like one had for K3 times K3. Like the motto would be, all those things that you did for K3 times K3, now you can do to more general Calabi-Yau fourfolds. In particular, you can search for flux vacua. Of course, it will be more complicated. They will have several branches that we have only analyzed two of them. The one that we call the generic scenario and the one that we call the linear scenario. But more than scenarios, these should be seen as branches of flux vacua. So the generic scenario is very well connected to well-known results on type 2b at large complex structure. This is what people have looked at. They take type 2b, they trace the dilaton, they take a large complex structure, and there where we have connected with the previous results in the literature. The linear scenario is the opposite. You take the axial dilaton, the weak coupling faster than the complex structure moduli, and then we have found that we can stabilize our moduli with a small flux-induced tadpole, just by connecting to these previous papers of Palti et al. The nice thing is that many of the lessons, I haven't emphasized this, but the one thing to convey before we finish is that many of the lessons that we learn in large complex structure, not all of them, but many of them, should apply to other asymptotic limits, like this philosophy and which things should happen. So perhaps this way of thinking can also help to obtain an overall picture of the theoretic flux blanket, combined with some of the others advances that other people have recently done, like we learned yesterday from Thomas talk. So thanks a lot.
Thank you, Fernando. All right, so is there any questions? Vera?
I had a question actually. Thanks for the talk. You know, it was very nice. I had actually a question and a comment. So the question is, in this large complex structure vacua, which you are finding with the tadpole, which is growing, which is basically constant as you increase the number of moduli, are they mirrored to some type 2A vacua, which one can control much easier? Because I mean, okay, you have all these quantum corrections, and there are all these things which but if you just look at classical equations and classical physics, they're kind of they appear a bit out of the hat. So I'm just wondering if you go to the type 2A mirror, whether I can understand these things as some nice clean classical physics as opposed to
What so you mean this type 2b1 or the other ones?
Yeah, the type 2b2.
Type 2b2.
The ones which violate the ones which don't work with the tadpole conjecture, the ones which are inconsistent. This one.
Yes, exactly. These papers in here are in type 2a.
And in type 2A, and can we see that in type 2A, for example, there's a problem with the tadpole? I mean, can we see that in type 2A, for example, as I don't know what the tadpole becomes in type 2A, and how the whole tadpole conjecture. I mean, I didn't think about how the mirror version of it is, but I'm sure there'll be something in type 2A. There'll be a dual of the type 2A tadpole conjecture. There'll be a dual of the tadpole conjecture in type 2A.
Actually, it's like in the Wolf et al. It's the same. If you remember, the tadpole of the Wolf et al is super simple. It's a product of two things. Well, here's the same thing. Is this guy? The only thing is that in here, in order to do mirror symmetry, we have to take very specific H fluxes because we don't want to miss geometry when we do mirror symmetry over 3 directions. So the H flux has to be orthogonal to the 3 directions that we. So it's a little bit more restricted than the Wolf et al. You also assume that you have a separation of field metric between the dilaton and everybody else, etc., etc. But these things, the tadpole and the solutions, they really work not exactly, but very analogous to the Wolf et al. So I mean, I would phrase it in terms of the Wolf et al, which again is ADS, right? But here, by assuming a particular metric, which is the metric of dual to type 2b, which is dilaton on one side and complex structure on the other side, you get Minkowski vacua. This is what Palti, Tassinatu, and Ward did.
Right.
And the comment is about, the explicit examples, because, okay, I mean, we try to work out, your models for a bunch of moduli, and, the tadpole conjecture is supposed to be for a large number of moduli. I mean, the whole spiel is that, for example, you need HT1 to be much, much bigger than all the other things. This is where we formulated it, and this is where the evidence comes. For example, if you look at the 7 brains and you uplift F theory, all the examples we built, they're in the large complex structure moduli, in the large number of complex structure moduli limit. And here, I mean, we try to work out some of your examples, but we could do 4 moduli at most. I mean, we couldn't do anything more than 4. So I'm just, and there's some problems with inverting the Saxions into axions. I'm just wondering if you have any comments on that, or if you guys tried anything more than 4, or.
I mean, no, we
For the explicit example, because I mean, there's a nice scenario, and it would be nice to understand, there's a scenario, but at some point, if you look, I mean, the same as with K3 times K3, there's a scenario that everything now works nicely. Then if you sit down and work it out, it doesn't work. So I'm just wondering if you have any.
Well, no, I mean, my only comment is that Palti et al. Already proposed an answer for. I mean, this is perhaps the most tricky equation, because I'm writing the solution in terms of the dual Saxion, so I need to make sure that I am in the Keller cone when I put some fluxes. Not all values for this guy will give me Saxions that live in the Keller cone, and this is something that I need to make sure. But this Palti et al. They were already aware of this point, and they propose in their paper a way to solve these things explicitly by taking some democratic answers. I don't know. And then, well, the only thing is that, again, these are the same equations of the Wolf et al. So if you find solutions for the Wolf et al. For arbitrarily large number of Keller moduli in type 2a, then you should be finding solutions in here as well, which I haven't done, and I don't know anyone that has done. But I don't know. I would honestly, I would be surprised if they didn't exist. It would mean that that the Wolf et al. Is only valid for a small number of moduli, which I don't have any reason to think of. But okay, I mean, to be completely honest, I haven't solved the problem. I don't know anyone that has solved the problem, and
we tried. I mean, we're trying, but
Wait.
stuck.
Let's continue the discussion after the second talk.
Okay.
We can keep going. So
okay,
let's thank Fernando again. Thank you.